Hello, welcome to this video. So in the last video we looked at Schrödinger's equation. We tried to use logic to derive it. We discussed what the wave function was. And if the wave function and Schrödinger's equation are unfamiliar to you, I'll put a link to that video down below this one. But what we didn't do much in that video is really use Schrödinger's equation to predict or derive anything. But we mentioned that Schrödinger's equation is very useful, and we gave some areas where, particularly in solid state physics, it can be helpful. Mentioned semiconductors, superconductors, and that kind of thing. But now I would like to show you how you can use Schrödinger's equation to achieve some quite cool things about, physical particles. And the most straightforward place to begin with that is looking at free particles. Now, free particles are particles which are not experiencing any total force. So right now, you're probably a free particle, unless you're watching this video whilst jumping in the air, which I wouldn't recommend. There could be lots of equations coming up, so you might get a bit dizzy if you do that. But you're probably a free particle. I'm a free particle. And free particles, because there's no resultant force, they don't accelerate. Which, tends to make them classically really boring. Classically, free particles are, probably the least interesting thing conceivable, but the bizarreness is in quantum mechanics. Not only are they absurd in their behaviour, they're remarkably useful. And that's because in quantum mechanics, free particles behave as waves. And so in this video, we're going to use Schrödinger's equation to mathematically derive the idea that free particles behave as waves. We're going to see how the size of the wave is related to the momentum of the particle. And then we're going to finish up with some applications of using the wave-like nature of particles, and particularly their ability to therefore diffract and form an interference pattern, to understand things about the microscopic structure or the atomic structure of materials. To understand materials at a really, really small kind of detailed level. And that's important if we want to understand things like how magnetic fields form. It's important if we want to build particular kinds of semiconductors, but we'll talk about that at the end. But this video will be about using Schrödinger's equation to essentially predict the wave-like nature of free particles. And then we'll finish up with some applications. This video is fairly impromptu in that I haven't put a huge amount of time into preparing particularly this one. However, done my best to put as much helpful content as possible. But I thought it was important to have a follow-up video to the last one, given that I want to show as many practical uses of physics and derive some of these as much as possible. Because quantum mechanics is marvellous in terms of the beauty of the mathematics, but it is also remarkably and almost ridiculously useful on a practical level. So we start with the assumptions we are going to make for this video. So we're going to assume Schrödinger's equation is true. It's worth saying that as an assumption. Often physical equations are considered as almost laws. Physicists have stopped using the term laws when describing new equations they come up with, because any equation will fail to work under certain conditions. Like Schrödinger's equation just doesn't work for relativistic particles. So, when I say assume Schrödinger's equation is true, although we can trust it under the conditions we're dealing with, it is an assumption. We are assuming that it works. But the free particles we tend to use for diffraction to understand the structure of materials, these particles tend not to be moving at relativistic speed, so that's a sensible consideration. We can use Schrödinger's equation without worrying too much about whether it's true or not in the context of relativity. The other thing we're going to assume is that the energy of our particle isn't changing with time. So that could be because the particle is experiencing a force, but that force isn't varying with time. So we have a time-independent potential. But an even more specific situation is where the particle isn't experiencing any forces at all. So where there's the potential is zero, such as for a free particle. And our goals using these two assumptions, so that Schrödinger's equation is true and that the energy of our particle isn't changing with time, is to firstly solve Schrödinger's equation fairly generally, so to come up with a general solution for psi of x and t, again assuming that it's the wave function of a particle whose energy isn't changing with time. And then we're going to look at a specific case of this where we're looking at the spatial part of our wave function for a free particle. Now, the spatial part is really the only part we care about for our free particle, because we're interested in, diffraction and interference patterns, and so we're interested in how the wave function is spread across space. We don't really care about the time dependence of the wave function for this video. So that's why we look at particularly the spatial part when talking about free particles. So those are our goals, and we're going to start with finding a general solution for our wave function psi of x and t to Schrödinger's equation. Again, we're saying assuming the energy of our particle is not changing with time. So, as we said, we're going to start with having a go at finding a solution to Schrödinger's equation, a fairly general one. Really with the only condition being that the energy of our particle is, fixed, it's not time dependent. Now, to do that, we could just solve Schrödinger's equation without really thinking about, the physics of the wave function or how to visualize it. But, I personally don't find that a very helpful approach when trying to understand what the wave function is doing. I think it's always good to use analogies with the physical world around us whenever possible. And so to do that, what we're going to do is we're going to take Schrödinger's equation, get a more useful differential equation for the wave function. And by more useful, I mean we'll be able to make an analogy, a comparison between our new quantum mechanical equation for the wave function and an equation in classical physics you're probably very familiar with. Most definitely if you've done A-level physics, and particularly if you've done engineering at university, you'll be very familiar with the classical equation we're going to use to get a visual picture for what this wave function is doing. And once we have the classical equation that we'll be able to compare to our quantum mechanical equation we're going to get, it will be clear how the wave function will have to change, allowing us to give almost immediately the explicit form that the wave function takes. So if we're thinking of helpful classical equations that might compare to quantum mechanical equations, we need to think about what's important in terms of how things evolve and change for a classical system. Well, let's think of a system for now as like a single particle. Well, in classical physics, what that particle is going to do, so the dynamics of the particle, is going to essentially depend upon the forces that particle is experiencing. Or, in other words, the acceleration of that particle. You know, if you're doing kind of mechanics in A level or at uni, the first thing you do is find the total or the resultant force on a particle and then divide that resultant force by the mass to get the acceleration of the particle. And you do that because the acceleration of the particle will generally tell you everything you need to know about what the particle is going to do. And the acceleration, as I say, you get from the force, and the force a particle is experiencing is generally dependent upon where the particle is in space. For example, if the particle is very far away from something that's producing a force, then at least for most forces, the particle, our test particle, is going to feel a small force, but as we move our particle closer to the source of the force or the field, then the force will generally grow stronger. So in classical physics, there's often a dependency between acceleration, in other words the force on a particle, and the position of that particle in space. And the natural dynamics of the particle, I mean, you can get from an equation concerning acceleration, but the acceleration will depend on where that particle is in space. So the most important thing to know for the evolution of a classical system is where that particle is, so position. So for a classical particle, the position of the particle is the dynamical variable. It's the variable that can change that the laws of physics are going to relate to. And usually in classical physics, the position of a particle is related to its acceleration, and through that relationship, using Newton's laws or using them in differential form to get differential equation, you can work out what that particle is going to do. Now in quantum mechanics, the natural dynamical variable, the thing that is changing, according to Schrödinger's equation, is the wave function itself. So, you know, if we're building an analogy between classical physics and quantum mechanics, we want, for our quantum system, to have a relationship between the second order derivative of the wave function with respect to time, which is kind of analogous to acceleration, and we want to relate that to the wave function, which is analogous to position. And when I say analogous, I mean the equations will work similarly, the solutions will be similar. You know, classical equations that relate to acceleration and position will have similar solutions to quantum mechanical equations that relate, you know, second order derivatives of the wave function with respect to time to the wave function itself. And that's what we mean by getting a more useful equation. We're going to be working towards an equation that relates a second order derivative in time of the wave function to the wave function itself. And that will allow us to make a good classical analogy where it's easy to visualise what's happening. So we start from Schrödinger's equation. And we start there because Schrödinger's equation contains the wave function itself, and we want our final equation in quantum mechanics to contain the wave function, which is like, has a classical analogy of position. But we want our quantum mechanical equation to have a partial derivative, well, a second order partial derivative of the wave function with respect to time, whereas Schrödinger's equation only contains a first order partial derivative. So to get a second order partial derivative, we just differentiate both sides with respect to time. And using the product rule, which works very similarly for partial derivatives and ordinary derivatives, we get this equation. And now we're going to use our assumption that the energy of a particle is not changing with time, or put another way, the partial derivative of E with respect to t is 0. And if we assume that, then one of our terms is going to vanish, because 0 times the wave function is going to be 0, doesn't matter what the wave function is, leaving us with this equation. Now, the bottom equation here in black almost has the opposite problem to the top equation in blue. So in the bottom equation in black, we have a second order partial derivative with respect to time, which we want, but it's related to a first order partial derivative in time, and we don't want that. Whereas the top equation relates a first order partial derivative in time, which we do want, to the wave function. Sorry, the top equation relates the first order derivative in time, which we don't want, to a wave function which we do want. So essentially the problem is, in our top equation and our bottom equation, we've got a first order derivative in time, and we don't want that, because it's very hard to think of a classical equation we can compare our quantum mechanical equation to if our quantum mechanical equation just has a first order derivative in time of a wave function. And that's because, in classical physics, if we're thinking of the classical analogy, well, because the classical analogy of the wave function is position, the classical analogy of the first order derivative of the wave function with respect to time would be the derivative of position with respect to time, which would be velocity. And it's very hard in classical physics to think of an equation, a natural equation of motion, which depends explicitly upon velocity. Because, as Newton's first law kind of implies, velocity is relative. So the velocity of a particle doesn't really fundamentally matter. Because the velocity will be different for different observers, even in classical mechanics. So the natural equations of classical physics don't directly refer to velocity. There's an exception where if we're considering charged particles in magnetic fields, but that's very much an exception, and that exception itself ends up having to do a lot with relativity. But anyway, so going back to quantum mechanics, we want to get rid of a first order derivative of our wave function with respect to time. But we can do that because Schrödinger's equation relates the first order derivative of a wave function with respect to time to the wave function itself. So rearranging, we can just go, if we have a first order derivative with respect to time of our wave function, we can replace that with just minus some constant times the wave function itself. And that's good because we do want the wave function itself. So if we can replace a first order derivative in time, which we don't want, with our wave function, which we do want, that's really good. So we go back to the kind of the equation we had at the bottom of the left-hand box, which I've just rewritten here. And now if we substitute a partial derivative of a wave function with respect to time for equaling minus this constant times our wave function, we'll get this equation. And this equation is really useful, it's really good, because it relates a second order derivative in time of a wave function to the wave function itself. And the classical analogy of that is going to be an equation that relates acceleration to the position of a particle, and there's lots of equations in classical physics to draw from to understand, how a classical system would behave if acceleration was related to position in a way that has the same form as how, here the kind of, second order derivative of a wave function with respect to time relates to the wave function itself. So we're going to look at the kind of classical equation we can compare with this kind of bottom quantum mechanical equation in blue to help us understand the solutions to this blue equation, which is a lot more useful than the Schrödinger equation we began with, because the Schrödinger equation we began with had very little in the way of classical analogies. So on the last slide we had a much more useful quantum mechanical equation than Schrödinger's equation, much more useful in the way of drawing a classical analogy. So that's what we're going to do now. We're going to draw this classical analogy, because then we can solve, well, we'll know the solution to the classical kind of equivalent equation, as close to equivalent as we can get in some ways. And then we'll just apply that solution to our kind of quantum mechanical equation. So this is our quantum mechanical equation. Now it looks scary because the wave function is quite unfamiliar to us, but the wave function is just the dynamical variable for quantum systems. And the dynamical variable analogously for a classical system is position, which is a lot more friendly. The position of a particle, we sometimes use x, but if we're more thinking generally of a particle moving in three-dimensional space, we're interested in its position in three-dimensional space, which we can think of as being given by, essentially a group of three numbers. So where it is in the x, y, and z directions. So we just put an arrow over the x to indicate that this is the position in 3D space, often represented with a vector. But if the arrow is confusing, just ignore it. It doesn't matter for our purposes. I put it there to keep the classical equation, applicable to 3D space, but it works just as well in a one-dimensional space. So if you don't want the arrow above the x, just ignore it. It's fine. Well, bearing in mind that position is like the classical dynamical variable and the wave function is the quantum dynamical variable, we can get an analogy. Sorry, I'm inventing words. We can get an analogy to our blue equation by just replacing the wave function with x, or a vector x. And this produces this equation, where, omega is a constant. Now, in quantum mechanics, this constant is E over h bar, but since E over h bar is a constant and we're just saying omega is some constant, we can just think of E over h bar as the same thing as omega. And we can do that because we said the energy of our particle is changing with time, so E is evidently a constant. And h bar is by definition a constant in quantum mechanics. Now, if we look at this bottom equation is the equation for a simple harmonic oscillator, because what it's saying is that the acceleration of a particle is such that the size of the acceleration, so the amount of force the particle is experiencing, increases as the particle moves away from its kind of natural position. So in other words, there's a force that is getting larger as a particle gets away from its natural position, and the minus sign tells us that this force or the acceleration must act in the opposite direction to wherever the particle has gone from its natural position. So if the particle is kind of moving to the left of where it would naturally want to be, there's a restoring force trying to push it back to the middle, so trying to push it to the right, or accelerate it to the right. And the further this particle gets from its natural equilibrium position, the larger this force becomes. So you have a restoring force where this force kind of gets larger as our particle gets further from where it naturally wants to be. And the solution to that is generally in A-level written as essentially a sinusoidal solution. So a sine function or a cosine function describing periodic behaviour of our particle. The essential particle goes back and forth thanks to this restoring force. Assuming that there's no energy being lost in our system, so there's no damping, but as we said, we're starting with the assumption that the energy of our particle is changing in time, so it's fine if our classical analogy makes that assumption too. Now, you might think that e to the I something is looks very different to a sine or cosine function, but you can build sine and cosine functions out of solutions like this. Now, it will turn out for the purposes of quantum mechanics that it's more helpful to just keep with our solution in this exponential form. But if it looks unfamiliar, it's because in classical physics you can use these solutions and kind of add solutions like this together to build sine or cosines. And you do that because in classical physics we're talking about the position of a particle which is directly observable, so the position has to be a function that gives you out a real number. And therefore it takes in real numbers, so there's no imaginary numbers appearing in a in a classical solution. Whereas in quantum mechanics the wave function can't necessarily be directly observed. In fact, if we take out face value, it can't be. And that's because we can calculate things like the probability, which is related to the size or the modulus of the wave function. But we can't observe the wave function itself. The wave function is just a description of the probability of a particle being at a particular location in space. So it's not a directly observable thing, just as you can't directly observe probability, let alone an object which, when you take its size, gives you something like probability. I'm simplifying a bit there, but the core thing is the wave function doesn't have to be real, and generally actually due to Schrödinger's equation won't be. So it's more helpful to just stick with complex solutions. Even in the case of classical physics, although in classical physics you can take these complex solutions and add them together in such a way that you end up with a real function. So we've essentially gone so far that we have our quantum mechanical equation in blue, and that's like a simple harmonic oscillator. The wave function is varying like the position of a classical simple harmonic oscillator would. And here are examples in classical physics of simple harmonic oscillators. So you have, for example, pendulum-like things. So be that something swinging a larger mass on a clock, or somebody swinging on just a swing, or a metronome. Other examples are masses on springs. There are plenty of examples of simple harmonic motion. In fact, if you have something that's stable due to the resultant force being zero, but there are forces acting on it, and you displace it slightly from its stable position, it will start to oscillate like a simple harmonic oscillator. Now, often that oscillation will die away very quickly due to damping, But as I say, we're not worrying about damping because we're assuming the energy is fixed with time, which for a free particle it definitely will be. So as we say, the total wave function psi of x and t essentially acts analogously to how position acts for a simple harmonic oscillator in classical physics. And so we just take the solution for the simple harmonic oscillator, so how our vector x relates to time t, and we just essentially replace x with our wave function, so psi of x and t, and we can still keep in omega if we want to, but omega for the case of our quantum equation is just E over h bar. We can see that if we can compare the blue equation here at the top of the screen with our kind of black equation at the top of our bottom box. We can see that omega and E divided by h bar are the same thing. Now, you might think that that essentially gives us just e to the I omega t, but it's worth saying that psi, our wave function, is actually a function of x and t. So, whilst the time-dependent part is going to be the same as our classical simple harmonic oscillator, there's also going to be a space-dependent part. But that space-dependent part doesn't actually vary with time. So providing we can factorise it out such that the time-dependent wave function, such that the time dependence of the overall wave function changes in the same way that the time dependence of position changes for a classical simple harmonic oscillator, then essentially we can just stick in a position part of our wave function, and this position we can write really as any function. It turns out for a free particle it's easy to go the spatial part of our overall wave function. We write as just e to the I theta x, where theta is some function, but since theta could be any function, we're really just saying that psi of x and t is equal to psi of t times psi of x, where psi of x could be any function, and psi of t is essentially acting like a simple harmonic oscillator. And psi of t has to, because the simple harmonic oscillator is to do with how our overall wave function changes with time. So it's concerned with partial derivatives with respect to time, which will only act on the time-dependent part of our wave function. It won't place any restrictions on our spatial part of our wave function. So I just summarised it here with what omega and theta are. So this is a fairly general solution. Now we're going to work out what theta is for a free particle, and essentially then understand what psi of x is. So if we break down psi of x and t into psi of t times psi of x, what psi of x would be for a free particle. So we have now a general solution for psi of x and t for a particle obeying Schrödinger's equation where its energy is a constant. Now we're going to find more specifically, so psi of x, so the spatial part of the overall wave function for a free particle. And that will tell us about the wave-like nature of particles. Well, we start with our general solution written here, and we notice that we can break this down using essentially rules of indices into this, and here theta of x is a function of just x, so we essentially have psi of x and t is some oscillating function of time t multiplied by some function of x, and so we can just say the overall wave function is equal to the spatially dependent part of our wave function times the time dependent part of our wave function. we've essentially said that we can split space and time dependency from each other. And that kind of makes sense, really. Because Schrödinger's equation tells us about the change in the energy of a particle. It tells us about how, the total wave function will change, in time, which depends on the energy. But the change in time is through a partial derivative, indicating that really Schrödinger's equation will just care about time dependence very separately to any considerations about the spatial dependency of our wave function. So Schrödinger's equation, by insisting on having a partial derivative in time and not at all relating that to any partial derivatives in space, is kind of going time, takes no notice of space, at least the wave function for a particle can be entirely summarised in terms of its change in time by a term that has no dependency on space. And so Schrödinger's equation implies that essentially time is acting very independently to space. And it's this idea that fundamentally makes Schrödinger's equation incompatible with relativity. Because in relativity, time and space are very much interlinked, at least when going from one observer's reference frame to another. Now, if you would like a more formal explanation for why psi of x and t is equal to psi of x times psi of t, particularly where we would expect that the overall wave function would be given by multiplying the spatial and time-dependent wave functions together, rather than say adding them up, I would recommend checking out the video on Schrödinger's equation, which gives more kind of intuitive justification for this by thinking about the relationship between the wave function and probability. But anyway, we can see that we can clearly split psi of x and t into psi of x times psi of t, and this will be a fairly general solution to Schrödinger's equation, where psi of x is e to the I times some function in x. But that's the best we can do without bringing in further assumptions, and further assumptions more heavily restrict the kind of particle we're talking about. Now we want to talk about a free particle, so we can now bring in more restrictions based on the physics of a free particle. But to do that, it will be helpful to go back over Schrödinger's equation in more detail, and consider Schrödinger's equation as essentially just an equation acting on the time part of our overall wave function, because Schrödinger's equation is only concerned with partial derivatives in time, so we can do that. And then we can look at that equation and use other ideas in physics to deduce how the position part of our overall wave function will have to change. And that will end up implying that the position part of our wave function, so our wave function in physical space, has wave-like properties. So if we rewrite Schrödinger's equation just in terms of the time-dependent part of our overall wave function, because we're just looking at the time-dependent part, the function going into Schrödinger's equation is a function of time only, so we can replace partial derivatives with time with ordinary derivatives in time, and we can just rewrite Schrödinger's equation like this. Or writing it another way, we can say that some differential operator called Hamiltonian, which is essentially proportional to a first order derivative in time, acts on our time-dependent wave function to give us the energy times the time-dependent wave function, or I should say the time-dependent part of the overall wave function. And what this equation therefore says is there's a particular natural connection between time and energy. because if we want to know the energy of our wave function, we only consider the time-dependent part of the overall wave function, and we also only differentiate with respect to time. Space is playing no role in working out the energy of our particle. And that's telling us something very special about the link between energy and time. So we know that our free particle is going to have well-determined energy, so it's going to, obey Schrödinger's equation. Or this eigenvalue equation in terms of energy. But it's also going to obey an eigenvalue equation in terms of momentum, because our free particle has a definite momentum. And we might ask, well, if energy relates to the time-dependent part of a wave function, what does momentum relate to? And as you might guess where I'm going, we're going to see that momentum relates to the spatial part of our overall wave function. So momentum P relates to psi of x, just as the energy E relates to psi of t. And you might wonder, physically, why that is. Well, the energy of a system really allows the system to change its kind of structure, or its microscopic state over time. For example, if you have a box of kind of gaseous atoms, so a gas in a box, and we're considering the atoms in the gas. Well, in a gas, the atoms have a lot of kinetic energy, and so they're moving about fairly quickly, and therefore if we could take a snapshot of the gas at an atomic scale at one moment in time, and we could take a picture of it at a different moment in time, those pictures will probably end up looking different. We have different photographs because the atoms will be in different locations. And so energy allows us to meaningfully talk about changes in time of a system. Whereas now if we go to the opposite extreme, and we think about a system which has no energy, well, because, for a system with no energy, there's no way for what the particles are doing to change with time. In fact, there's no way for the particles to do anything. The system will be static and unchanging, so it will look the same in one moment of time compared to even if we waited billions of years later. And so because of that, really energy allows for a physically meaningful passage of time. In some ways you can't have time without energy. Now similarly, the position of a particle in space will change only due to a particle having some kind of momentum. Now you might think velocity is a more natural thing to link to position, considering how position changes, but it turns out that actually momentum is more fundamental, particularly if you're considering things like the movement of photons, which don't have any mass but still have some kind of well-defined momentum. Momentum ends up being much more meaningful than things like velocity. But even in classical physics, if you know the momentum and position of a particle, you can then easily work out how it will respond to any forces it's experiencing through Hamilton's equation. So there's a natural link between momentum and position, which is very analogous to the link between energy and time, and we can exploit that. And if you want a formal justification, you can use relativity, but if we exploit that link, we can essentially go from psi of t to an equation for psi of x by just replacing t with x and e with p, because p relates to space in the same way e relates to time. Now you might notice a minus sign has appeared. That minus sign is really due to the relativistic, formal underpinnings of this idea. It's really because the relativity justification, which really formalizes what I said just now, is that you can kind of match the time-like and space-like components of form momentum with the time and space-like components of form position, and doing that matching allows you to match energy with time and momentum with space, but also because form position and therefore form momentum are naturally a kind of vector called a contravariant vector. Because of that, it turns out that actually when jumping from relating time-like components, so when jumping from comparing E with T to comparing space-like components, so comparing P with X, we have to introduce a minus sign. So it's ultimately due to relativity, but if the minus sign confuses you, don't worry, it's very much a technicality for what we're doing. It doesn't affect the final form of our solution. But it's worth mentioning relativity for those interested in a more formal justification, and I would recommend checking out my relativity playlist if you would like to know more about form position and form momentum, particularly form momentum, because there's a whole video talking about form momentum and what it is. But anyway, for our purposes, moving back to quantum mechanics, we now have a equation that relates psi of x to p. So relates to the wave function of our free particle in terms of physical space to the momentum of that particle, and that's an eigenvalue equation in terms of momentum, which we would expect because a free particle has well-determined momentum. Essentially, if we solve our eigenvalue equation or our differential equation, we can say that psi of x is just E times it's just E to the IP over h bar times x. So essentially psi of x has a periodic or oscillating like nature in much the way that the position of a simple harmonic oscillator will oscillate back and forth. Or in other words, psi of x is kind of oscillating, and so psi of x is describing a wave. But this wave is oscillating, not with respect to time t, but with respect to spatial position x. And so because of that, p is telling us not about how rapidly the wave changes in time, but p is telling us about how rapidly the wave changes in distance x. So p is relating to the wavelength of the wave. And it turns out, if you go through the formal analysis of looking at waves, that due to our kind of wave function we have here, if you increase the momentum of a free particle, you'll actually decrease the wavelength of the free particle. So not only have we derived that a free particle should act like a wave in terms of its wave function in physical space, but we've shown that we've got an equation that shows that as the momentum of the particle increases, the wavelength will drop, and thus explains why wave particle duality isn't observed for macroscopic objects usually, which have a lot of mass and therefore generally a very high momentum. Now you might go, what happens if we make the momentum of even a really massive object small by making it move very slowly? Well, then it would take ages to cover any distance. Meaning if you wanted to pass it through something for it to diffract, it would take a very long time to pass through that thing. For example, if a dog wants to use quantum mechanics to diffract around the trunk of a tree, then taking the average diameter, or estimating the average diameter of a trunk, the dog would end up taking longer than the current age of the universe just to get around that tree. That's how slowly they would have to move for their momentum to be tiny enough to give them a large enough wavelength for that wavelength to be comparable to the trunk of a tree, or the diameter of the trunk of a tree. And so we've both shown wave-particle duality and explained why we don't observe it for macroscopic objects. And if you want to, you can go from our equation for psi of x and actually derive the de Broglie wavelength, which explicitly relates the wavelength of physical matter to the momentum of that physical matter. So a cool little exercise to try if you want. But the key thing is, essentially, we've shown that a particle, when moving freely, will indeed behave like a wave, in terms of its wave function in physical space. So now we've looked at the spatial part of the overall wave function, and we've seen how that predicts wave-particle duality. Let's look at actually using the idea of diffraction of particles in more detail. Well, because of the velocities subatomic particles can easily be made to move at, and their relative masses, it turns out that, subatomic particles have the wavelength we would really need to look at the structure of materials at an atomic level. So by looking at how free particles diffract through the spacing between atoms or molecules or ions in the material, we can tell a lot about the structure of that material, so how those ions or molecules are arranged. Now that's really useful if the structure has some general kind of symmetry, or at least in particular regions has symmetry. So it's very useful if we're looking at kind of ionic substances, metallic substances in a solid form anyway. It's not so useful if we're looking at disordered solid structures like glasses, or if we're looking, well, if you consider glass as a solid, it's slightly complicated, the states and matter of glass. But, glass is fairly disordered, so, we can't really tell much about the structure of glass through particle diffraction, but there's a lot of substances, at least in solid state physics, we can tell something about. And really, particle diffraction is the main way to uncover the microscopic structure and arrangement of kind of macroscopic ordered structures. And it's also helpful for looking at the impact of defects, because we can use particle diffraction to identify where the defects are and how those defects are distributed, and then we can use our kind of experiments to see how the defects have affected the macroscopic behaviour of our sample, and linking the two we can then relate microscopic structure to macroscopic properties and see the influence of defects there. But not only in terms of impurities and also the growing of ordered structures like semiconductors, there are other kinds of structures we might be interested in looking at that relate directly to microscopic states of a material. So one thing is magnetism. So if you see my video on quantum spin, you'll know that certain elements are naturally magnetic, or that atoms are naturally magnetic, because electrons having quantum spin essentially generates a magnetic field. However, for most substances, the atom's magnetic fields are aligned randomly and there is no overall magnetic field for the structure. But for a particular class of material called ferromagnets, if you put those materials in a magnetic field, not only will the material become magnetized, so the atoms will align their magnetic fields, but when you move that magnetic field away, the alignment of the atoms will stay. And that's because for those materials, aligning magnetic fields is actually going to make, contrary to what you might expect, the energy of that object less than if the magnetic fields were randomly aligned. And that's to do with degeneracy and kind of rules in quantum mechanics that I might cover at some point. But essentially, a structure that is magnetic has a symmetry, albeit in the magnetic field. And if that structure begins to lose its magnetic field, so you heat a ferromagnet, then essentially that uniform magnetic field breaks down into regions of a material where in each region there's a uniform magnetic field, but the uniform magnetic field from one region to another might differ. And we call these regions magnetic domains. So, if you're heating up the ferromagnet, its decaying magnetic field will be described by the breakdown of the symmetry into kind of pockets which are in and of themselves symmetrical, but which don't have symmetry between them. And we call the formation of symmetry or the breakdown of symmetry a phase change. So actually, a ferromagnet being magnetized is it changing phase. We often think of phase changes to do with changing states of matter, and that's an example, but by far it's not the only one. So magnetism is to do with phase changes. Also, the existence of mass for particles is due to a phase change in the Higgs field early on in the universe. So phase changes are very general and rather intriguing in physics. And you can analyse this phase change by seeing how electrons diffract through a material, because electrons are charged, so they'll react to a magnetic field, and so the diffraction pattern you'll see will tell you about the magnetic field of the sample and how that magnetic field might be changing. And due to the wavelength of kind of freely moving electrons that we use, we can see how the magnetic field might be breaking down into domains at a kind of like microscopic scale where these domains are apparent. Because we don't see those domains at a macroscopic scale. These domains tend to be really tiny. So we can understand magnetism and the formation of magnetism or the breakdown of magnetism through looking at things like particle diffraction, and that's very useful because it can give insights into how things like the Earth's magnetic field forms and how it might one day cease to be. In fact, we expect the Earth to one day lose its magnetic field. That's going to be long after you or I die. Very, very, very long way from now, so it's nothing to worry about. But in terms of understanding how long that might take exactly, and what processes might slow it down or speed it up, understanding magnetism is very important, and understanding how it forms, and ultimately to understand how it forms, we need to look at the formation of symmetrical magnetic fields, or an overall symmetry in the magnetic field at an atomic kind of scale, and we can do that by studying the formation of magnetic fields in ferromagnets and passing electrons or other subatomic particles through these ferromagnets as they're becoming magnetized. And also ferromagnets are very useful on an industrial scale because we use ferromagnets, in things like transformers, which are responsible for being a huge part of the national grid in terms of allowing electricity to reach the voltages it needs to be transported, and also for the voltage to change such that when you use the electricity at home, you don't get a huge there isn't, as much electricity running through kind of, wires in the house. So, the idea of, particles diffracting might sound rather abstract, it might sound like it doesn't have many applications, but, as with everything in physics, although the maths might be for its own sake beautiful and intriguing and in many cases bizarre, it is incredibly useful to understand the physical world around us, and you can use particle diffraction, of subatomic particles to understand things like geomagnets and the formation of magnetic fields for planets and how planets can gain or lose their magnetic fields. So, and given magnetic fields are crucial for life, it could be that particle diffraction could play a huge role in our understanding of what impacts the formation of life on other planets, and therefore in astrobiology. So, has lots of applications already. Particle diffraction does, but it might have many more in the future too. But anyway, this has been, a fairly impromptu video in some ways. But I wanted to get this video done shortly after the last one because I feel it's always important to show how we can use equations to work things out. And if at all possible, to go through the mathematics as well. So I hope this video has been helpful. Hopefully brought some new ideas to the table which you might not have seen before. And I'll put a link to the video on Schrödinger's equation and also a link to the relativity playlist below this video. But as always, I hope your day's going really well. Hope you have a really good week, and hope to see you for more fun physics soon.